There's a Hawaiian term for a sense of place. It's called ike. We had this in mind when we built the Energy Lab and designed it to fit into the space, to integrate into the environment and to the campus as a whole. What you may notice if you spend any time on the HPA campus is you'll notice that the chapel and the Energy Lab on opposite ends of the campus have a tremendous resonance with each other. One element of this is the ohia post that's behind me. The chapel has many ohia posts at the west end of the chapel. We found this large ohia post fallen in the woods above Hakalau. The other thing that you might notice is the concrete walls have large stones embedded in them. This is board formed concrete. This is an idea of the architect Asipov when he designed the chapel. Asipov's vision or metaphor for these rocks was that they represented our students that come to us with sharp edges and that we shouldn't shave them all off. It's a really neat resonance with the campus. It resonates with the environment. As you can see behind me, the mountains. There's a wonderful view here. It's a comfortable place to be, but most of all, it fits in the space that it occupies. But this room is interesting for several different points. Number one is the shape of the building. The shape of the building can be very clearly seen by the wing shape behind me. You can also see that these walls are fairly smooth, and this is part of the passive ventilation system that we have here at the Energy Lab. To conserve energy, we don't air condition and we don't use fans unless absolutely necessary. But what we do have is we have this ventilation system that's driven by the wind. The wind at this site is about 22 miles an hour on average over the year. This room has concrete countertops. It also has a concrete conferencing table. It's also the center for our outreach efforts because we have two video conferencing setups in this room, a television and a camera on one side of the room, a television and a camera on the other side of the room, which is unusual. This is the first time this has been tried. The people on each camera can see the people on the other camera, and they can see the people in the middle of the room. This gives us the unique capacity to be a translator for someone who has perhaps iChat or Skype on one part of the world and then maybe using PictureTel or Tandberg on another part of the world. We can actually act as a translator site for these people while engaged in the conversation. The acoustics in the room are very, very nice. We've got sound dampening panels up in the air on the upper parts of the wall to keep the echoes down. The floor connections for the tables are made out of the cutoffs from an ohia tree. The exact same ohia tree is used to support the west side of the building. So there's a sense of structural continuity through this building. If you wander through, you'll see the same sorts of things coming up. The same themes will come through. Two compelling and exciting things have happened at the Energy Lab recently. 6 weeks ago, we were awarded the American Institute of Architecture Lippman Award for the State of Hawaii chapter for the AIA. We also won the Editor's Choice Award for the building. The poster for that is behind me here. We went to a 300-person awards banquet, and the architects in the state of Hawaii were very inspired by the work that we've done here. The other thing that's very, very exciting for us is that yesterday we were awarded the first LEED for Schools 2.0 Platinum Award in the state of Hawaii. We're the #4 school in the entire country to be able to reach this specification. It's incredibly rigorous, and to give you a background on what LEED is about, LEED is Leadership in Environmental and Engineering Design. And what we've tried to do here is create a space that's comfortable, it's energy efficient, and it meets the LEED specifications, which for schools include how habitable the school is, how much the building is used as a learning and a teaching facility, how it integrates into the curriculum. It's very, very rigorous, and this is why only 4 schools in the country have been able to do this so far. The Living Building Challenge is that we have to demonstrate that there are no toxic substances in the building. We have a long list, which is called the Red List, which when we worked on the project, we all had to memorize. The Red List includes such abstract things as cadmium and arsenic in the monitors. We worked with Apple Computer to have special monitors that have no arsenic and no cadmium, no heavy metals. And the computer boards inside can't have brominated flame retardants, BFRs. This is a cutting edge thing for Apple because they're in a huge, huge movement to demonstrate environmental sustainability in construction of products. They also have what's called cradle to grave responsibility, so that if we buy a laptop from them, like the aluminum laptops behind me over here, when we're done with those laptops, we turn them back to Apple and they recycle those and turn them into other laptops. They take care of all the heavy metals, or if there are any toxins or any substances in these devices, they take care of that. This gets even larger though. This building has special glue in all of the glulam beams. There's special glue in the furniture. There's special glue in the carpets. The carpets that I'm standing on right now are made out of prairie grass that was never touched with a herbicide or a pesticide, and they're lined by unbleached cotton. There are no chlorines allowed in the building, no any insecticides, no PVC, which means the entire plumbing system and all the electrical system had to be done in steel or in high-density polyethylene. We don't have the maintenance costs associated with normal buildings, which are done very quickly, cheaply with 1950s engineering technologies. Heating, ventilation, and air conditioning systems with toxic substances that are built to waste energy because it's easy. We've done the homework and figured out how to do this, and it's a little bit more thought-provoking, but the end result is a building that's comfortable to be in, it has a low impact on the environment, and in the long term it will cost the occupants much, much less money to occupy. This is the monitoring and control lab, where we actually monitor energy use and production for the entire energy lab, but also energy use on the entire HPA campus. Behind me are some displays that monitor carbon dioxide in the different closed rooms. As you can see, these are all percentages of ambient carbon dioxide in all of the closed rooms. We've simulated a lot of people being in this room with the windows closed, and what you might see is one of these monitors might change and then it turns red. What you may also notice, if you had very, very good hearing, is you would hear the louvers open in this room. This is an example of the active environmental control in the building without using air conditioning. So we have a lot of monitor stuff here that we can monitor trends, but the real analysis doesn't happen automatically with computers. It happens with the students who actually analyze this data and try to find out what is really going on with the building, what's happening on a daily basis, on a weekly basis, on a seasonal basis. And this ties in with the environmental monitoring system. The other things that we have in this room are weather stations that monitor photovoltaic solar input, so it measures the amount of solar radiation we have, and wind power, so that we can calibrate how effective the building is at capturing sun and turning it into energy, and wind and turning that into energy, so that we can do further expansions on our renewable energy resources here on campus. This is a one-stop shop. If you look here, you can tell if all things are green, the building is well ventilated, it's comfortable, it's within certain standards for CO2 and certain environmental conditions that we have. The water reservoirs are full, the power use is all okay, and the computer systems are running very nicely. We can also access the lighting systems from this. As I said before, you can get this from a phone. We can control it over the web. We can monitor the water catchment systems, and it's fairly sophisticated. So if I go through the screens, you'll see that on this screen here, we have a screen that shows all the ventilation surfaces, windows, louvers, and fans. And if this is active, they have green icons showing that air is flowing through. But the message here is environmental control can be done in a very, very smart way using very little power, and can be a model for how buildings can be safe and comfortable places to live and to learn. I'm standing in front of the water catchment tank for the HPA Energy Lab, a 10,000 gallon concrete sprayed tank that was actually constructed in Puna, about 90 miles south of here. It's used to catch all the rain that we catch off of the roof, a 6,012 square foot roof. To give you a sense of what the scope of that is, for every inch of rain that we catch, we get 390 gallons of water in this tank. We have tracking methods that measure the amount of rain that's captured in these black tubes right here, how much goes into our first flush diverter, and then how much is captured in the tank. I'm leaning up against a blue tank, which is our pressure reservoir for all the faucets and toilets and sinks in the building. What happens with this tank is this is pressurized with compressed air, and once or twice a day, a pump runs on the top of this and pumps the water against the compressed air, so that we don't have to use energy every time someone flushes the toilet or washes their hands. Behind me over here are some of the gauges that you might see if you were monitoring the system. If you looked at this gauge right here that has the red numbers on it, this shows us the amount of water that's being used down to 1/10 of a gallon. Now, 1/10 of a gallon is not very much water. We have another meter right behind me up here that's in this group of colorful things that's accurate down to 1/100th of a gallon, which is 15 drops of water. If we have a leak in the tank, it shows up on sensors on top of the tank. If we have a leak in this system, it shows by both pressure and by flow. If we have a leak in one of the faucets or one of the sinks or the toilets in the building, this will also show on our meters. It's so complex that if we have a leaking faucet in the middle of the night, this orange valve up above me will actually turn off the water for the whole building to conserve our resources. The real message here is that it's not just catching resources like energy or water, it's shepherding the resources that you have so that you're not wasting anything. We throw a tremendous amount of resources away in our culture because we've never had to conserve. This is an example of one of the ways that we can be conservative with those resources. Not just to save money, but because those resources are becoming more and more scarce as we go along. One of the things we've tried to do with this Energy Lab is to do the best practices and to go a little bit beyond what are the best practices or what are accepted norms. One of these is an experimental radiant cooling system, the panels for which are behind me. They're solar panels without the cases, and they radiate hot water out to space and into the wind at night. We use this cool water to cool the computers in the monitoring lab and the rooms in the north side of the building. Behind me is an insulated tank full of very cool water. We keep the water in this tank cool with soy foam insulation, which looks like this, made out of soybeans and catalyst to make it into about an 8-inch layer on this that has an insulation value of about 22, higher than normal home insulation. This modified air conditioning system, or radiant cooling system as we call it, is experimental, uses about 2% of the energy of a normal air conditioning system, and is one of the things that we're using as a strategy to minimize the amount of energy that's expended to run the building. A 6,000 square foot building like this would have an air conditioning load of several hundred or $1,000 a month. In our case, due to passive ventilation and the use of this radiant cooling tank, we've kept that almost to a zero number. It's really one of the experiments that we're trying to do here, high-tech stuff with low-tech equipment, well thought-out solutions, and in a cutting-edge way to conserve energy that we hope will be a mark for the future. This is the outdoor classroom, as you can see. It's got places for students to sit, a whiteboard for them to do their projects. And the other nice thing is that you notice that many of the counters in the building are made out of concrete. It's an environmentally sound medium for us to use. It didn't have to be transported on a boat or on a plane. The other interesting feature about this is that if you look carefully, you'd see the outline of the mountains behind the wall. This is done by taking a picture, a panorama of the entire mountain range, and then in etching this into the concrete feature. It's a comfortable space, and what I've noticed is people will come up here to do things that have nothing to do with the Energy Lab. Play music, work out dance routines, exercise. It's a really nice place to hang out, even though it's a little bit distant from the rest of the campus. This workshop is an example of the kinds of things that we actually do here in the lab. Behind me next to me is a telescope, which we use for evening viewing. We have integration with the iPads and the iPhones that we have here so that we can actually control the telescopes using the iPads. The iPads work as simulators when we're working in the evenings, or times when it's actually cloudy or daytime, so kids can learn about astronomy even when it's not nighttime viewing. We also have demonstrations for wind power. We have certain labs that we're doing in this room on soil studies. We're doing biofuels experiments on bioethanol and biodiesel. We're doing other experiments on solar panels, evaluating solar panels to find out which are the most efficient, which give you the better bang for the buck. All of these really point to how do we develop renewable energy resources. Behind me is a parabolic dish that we got from one of the microwave companies. We're going to use this as a template for making solar ovens that in this region of Hawaii will actually produce about 5,000 watts, or about more than most ovens, of power, solar oven power, in an area about the size of a loaf of bread. This is one of our projects that we're hoping to export to third world nations so that we can come up with simple tools for common problems in third world nations. The projects that the students do in this workshop are hands-on, they're authentic. We hope that the kids feel a sense of ownership, that they invent their experience, because in the end what we're trying to cultivate here are change agents, students that will go out and actually change the world, and that's what the real mission of the Energy Lab is all about.